this fourth lecture in lecture series on aerodynamics, especially meant for students, those who are willing to appear for willing to go for higher education or willing to appear for GATE examination. Also, students, those who are actually looking for job opportunities, these will be concepts will be very helpful. So, in today's class, actually, we are going to talk about one of the most important concept of aerodynamics and fluid mechanics, which is called a boundary layer. So boundary layer is a important phenomena when we are trying to understand the behavior of a flow over a solid object, and when the flow actually passes over a solid object, it plays very crucial role for the flow to remain intact to the surface of a solid. So what is basically a boundary layer? Like we have discussed in our previous classes, boundary layer is basically a very small and very thin region which is in the vicinity and close to the surface of the solid object. In this figure we can see close to the surface of an aerofoil. So this region plays a very important role in changing the velocity of a fluid and making viscosity effects dominant, particularly when the flow interacts with the surface of a solid. Immediately on the surface of a solid, the velocity actually goes to zero. This condition is actually known as no slip condition, which is very helpful while analyzing the studies in using softwares. The boundary conditions, that is what is called as. So in this region actually the velocity varies, velocity changes from zero on the surface of a solid. Velocity changes from zero, which is also termed as no slip condition, from the surface of solid to the free stream velocity. So basically it is the distance over which the velocity tries to regain its initial value, and the viscosity therefore becomes important. As you can see, the velocity keeps on increasing constantly following a certain pattern, so that we are going to see. And so this boundary layer is an important part of, like I told, what causes the flow to remain intact or attached to the surface of a solid, right? And outside this boundary layer, because the velocity variations are not that much important, or the all velocities move with a free stream velocity, flow moves with a free stream velocity. So the region outside this boundary layer is treated as an ideal flow. Generally, when we study aerodynamics and fluid mechanics, we have two basic ideologies. Sometimes we treat the flow or consider the flow as an ideal fluid, and many times we try to investigate what happens in the boundary layer when the flow moves over the surface of a solid. So that this region where the viscosity effects are important is termed as a boundary layer. Then coming to there is something called velocity profile. So based on experimented investigations, it has been found that especially for laminar zone, actually the flow in which the boundary layer within which the flow remains laminar, the boundary layer actually, the velocity variations actually follow this kind of a profile. This is known as a parabolic profile. Okay, so you can see that this velocity profile is basically measuring the velocity at certain intervals from the surface of a solid, or at certain distances at fixed interval normal to the surface of a solid till the maximum point or free stream conditions are actually reached. So this region actually is known as a boundary layer thickness, in which the velocity actually varies from zero to free stream velocity, and the curve which is obtained by joining the velocity. So for example, let's say we have one point here, another point here, and third point here, and fourth point here. All these 4 points actually we have let's say connected an apparatus which is able to measure the velocity, and when we write these velocity in vector terms, it appears to have some arrows, something like that. Now connecting the tip of all these arrows starting from the zero velocity point, the profile that we have obtained, this profile is actually known as velocity profile. So it is important to study velocity profile, especially when we talk about flow between the parallel plates, flow between the pipes. It's important to have the knowledge of this velocity profile so that we can see where the flow is actually getting affected. If some problem arises, how to get rid of those problems if it is inside internal to the pipe. And the free stream velocity, you can see that, like we talked about the flow, it takes time for the flow, or actually it takes certain distance for the flow to get back to its normal state. The free stream air, when it comes in contact with the surface of a plate, the air gets affected, the flow velocities actually decreases, like we discussed, zero on the surface of a solid, and it takes certain time for the flow to actually regain its initial velocity, and certain distance, time over the length and distance over the normal to the surface of a solid, to come back to its initial stage equal to free stream velocity. So this small region whereby the velocities are getting affected, because the velocities are affected, the viscosity becomes a very, very important parameter or factor, which is important for all kind of considerations, especially when we talk about shear and stresses developed on the surface of a solid, especially in structural mechanics when we talk about. Then boundary layer is actually the idea was first introduced by Ludwig Prandtl, one of my favorite scientists actually. Ludwig Prandtl actually have observed, and he came up with the idea of boundary layer in order to relate the potential flow theories and the flow actually observed on the surface of a solid. And then he derived the equations from the Navier-Stokes equation, which is also termed as one of the most difficult equations in fluid mechanics, and yet to be solved completely, and the exact solution has not been attained yet. So Navier and Stokes equation actually was simplified by the Ludwig Prandtl, and for a steady two-dimensional laminar, steady means basically the flow pattern is constant over time. Two-dimensional, we are not looking around the thickness of the plate, we are simply looking at a side view of a plate, and we are trying to study laminar incompressible. Laminar means the flow velocities are actually within certain range, or the flow behaves like sheets or layers of the particles moving in a discipline order. So incompressible flow, basically the density is actually maintained constant and at no particular point of a time the density is changing. So Ludwig Prandtl actually tried to simplify the complex Navier-Stokes equation under these assumptions, and he came up with certain equations which is given by actually which is given by these equations, fine. And this is what we have here. So we can see there is no time derivative for the steady flow, two-dimensional flow, because we have x and y components, and incompressible means density remains constant. So everywhere the density can be seen outside the brackets or not appearing in the derivatives. So this is basically a two-dimensional equations for the study of boundary layer on a flat plate, right, which is one of the most important when we, and only these kind of equations are solved in all kind of softwares, and everywhere we are trying to use the software support or numerical methods. We are trying to approximate the solution close to the exact solution, fine. Then coming back to the flow behavior on the flat plate, right, the flow when it comes in contact with the free stream flow, when it comes in contact with the surface of a flat plate or maybe surface of a solid, the flow gets actually accelerated, like we have seen. The flow when it comes in contact with the surface of a plate, it is accelerated, the velocity keeps on decreasing along over the length of the plate. So we can say that the Reynolds number at any point or any distance from the leading edge of the plate can be calculated with this equation, whereby x is the distance from the leading edge of the plate. And as you can see that because the velocity keeps on increasing, the inertial effects become important, and the flow tries to automatically, because inertia gains the dominance over viscosity, the flow leaves its laminar behavior and tries to transit into turbulent region, where the particle velocities they don't follow any pattern and they move randomly motion. So this region of flow transition is of quite important when we talk about flow over aerofoil. If we could restrict the flows to laminar region at any given velocity, the devices that we have designed, the equipments that we have actually designed as an engineer will be highly efficient and will give 100% response or the desired performance, right? So when the flow starts behaving, or when the flow comes in contact with the plate, like I said, it gets accelerated, and because of the increase in velocity, it changes from laminar to turbulent flow. But before turning into a turbulent flow or turbulent region, like you can see here, there is a certain gap. Okay, so this region is actually very important. All the scientists and engineers around the world, they are trying to delay work on delaying this cause, or before reaching to this 3 into 10 to power 6 value of Reynolds number. So basically this point whereby the flow starts to transit or tries to become turbulent in nature, the Reynolds number at this value is called critical Reynolds number. So beyond this critical Reynolds number, actually the transition phase from the ordered pattern to unordered and random pattern, this transition phase actually takes place at critical Reynolds number for a flat plate it comes around 1 into 10 to power 5. Okay, and at this point where the transitions actually happen to occur, or the flow tends to become turbulent in nature, the Reynolds number could be obtained is 3 into 10 to power 6. This Reynolds number actually has been also experimented by Reynolds, Osborne, Reynolds, and he found out that there are certain behavior particular to the Reynolds number which can be actually classified. Based on the Reynolds number, you can classify the flow or divide the fluid flow into different types. So here we talked about, so here the boundary layer can be observed to exist in 3 regions: a laminar region, a turbulent region, and a phase over which, or a certain length over which, this transition actually takes place. So the transition are not immediate. Okay, particularly if the flow is happening at velocity such that it reaches automatically at the leading edge 3 into 10 to power 6, there will, instead of laminar region, we will definitely have a turbulent region directly appearing here. Or maybe if it starts, the object starts flying with a speed, or the flat plate moves, or the air over the flat plate moves with a velocity corresponding to the critical Reynolds number, we may not even see the laminar region. Directly we'll see a transition region, and then it will lead to the formation of a turbulence. So see, this transition phase and this laminar and turbulent boundary layer particularly depends upon the velocity with which the flow is moving. If the flow is starting with low velocity, we can observe the formation of laminar, transition, and turbulent region. If the velocity is corresponding to critical Reynolds number or this turbulent boundary layer, definitely we won't be able to see the occurrence of laminar and transition region. Then coming to boundary layer over aerofoil surface. Over an aerofoil surface, actually the flow, when the flow moves over the curved surface, aerofoil surface generally have an upper curved surface. Under certain special conditions, special design criteria, we have this upper surface a little bit of flat. Over the curved surface, actually when the fluid moves over the surface, it is the difference in velocity or the pressure gradient between 2 points which accelerates the flow to move forward, right? By the as the final velocity, as the flow moves over the surface of a aerofoil, at certain point it is quite possible the velocity at the front position will be lesser than the velocity at the rear position, the backward point, right? So in this region actually flow reversal takes place. So this region is actually flow reversal, the point where the pressure actually is less than the atmospheric pressure. So the atmospheric air tries to enter into the region to interfere with the flow which is actually taking place on the aerofoil surface. Here you can see the velocity gradient in y direction perpendicular to the flow. The velocity gradient is greater than 0. That means the velocity is at other position, or the velocities they are greater than the 0. Okay, so second value is less than first value, and first greater than the second value is actually less than greater than the first value. It is because of the pressure difference. The difference of pressure actually pushes the air to move over the surface of aerofoil attached to the surface of the aerofoil. Now, two things which are very important when we talk about flow over the aerofoil. First one is favorable pressure gradient. Okay, so favorable pressure gradient is basically the pressure values which accelerates the flow. Here you can see that the difference of velocity is less than 0, and then when we talk about pressure, here the pressure gradient will be actually here the velocity gradient is greater than 0. That means the pressure gradient is less than 0. That means the pressure at forward point is less compared to the pressure at the rearward point, at the backward point. So this causes the flow to get accelerated, and the point will come at a certain point the pressure gradient will become close to 0. That means it becomes very difficult for the flow to move forward because it has no what you can say driving force or the driving mechanism. Here the pressure is the driving mechanism which causes changes in the velocity, and the favorable pressure gradient actually causes the flow to accelerate. Instead, in place of that, if we have adverse pressure gradient where the pressure at the forward point is less compared to the pressure at the rearward point, this leads to deceleration. Sorry, that's a mistake. It should be deceleration of a flow, and the flow gets reversed. In place of moving forward, like I told you, the external flow tries to interfere or interact with the low pressure air on the surface of a solid, right? The favorable and unfavorable pressure gradients can be represented by means of these derivatives, right? Then why it is important, the adverse pressure gradient and the deceleration of a flow results in flow separation, forming a separation bubble on the surface of the airfoil. So these separation bubbles actually sometimes they start from the leading edge at high velocities, and sometimes it start from the trailing edge because of the flow acceleration and inertial effects, and they result in they cover at high angles of attack and or at high speeds, high velocities. These flow actually tries to remove or detach the upcoming flow, and results in flow separation with a heavy loss in lift and then increase in drag of the aerofoil surface. Now there are certain terminologies which is important when we try to understand the boundary layer. The first one is known as displacement thickness. So what is a displacement thickness? Displacement thickness has to deal with mass flow rate, right? Displacement thickness is basically the thickness or the distance by which this streamline, the outermost streamline, need to be shifted so that we can account for the loss which is happening because of change in velocity. If the free stream velocity is here, but because of the presence of the plate, because of the formation of a boundary layer, there has been a change in velocity, so the mass flow rate has decreased over the entire region in order to understand, so account for loss in mass flow rate because of decrease in velocity. So we can see if this is basically a straight line, actually this velocity represents a free stream line. We want all the velocities still the surface of a solid to have the same value, so losses are actually counted in this particular region. So this is the loss in mass flow rate over the thickness of the boundary layer, and displacement thickness actually takes care of losses. So by how much distance actually we should add or displace this boundary layer so that our mass flow rate, which was initially in this region, whichever value of mass flow rate we have to attain the same mass flow rate, okay, to have the uniform conditions, what would be the displacement of this outermost boundary line. The formula for calculating this displacement thickness can be represented like this, whereby you have the local velocity in comparison to the free stream velocity, and we have to integrate this over the entire distance from 0 to infinity, and probably till the boundary layer thickness here. Then coming to the second important concept, which is momentum thickness. Like displacement thickness, momentum thickness is again a mathematical and hypothetical idea whereby we look for momentum losses. How much momentum losses has occurred in this region because of decrease in velocity, and to have the same value of momentum, linear momentum over this particular region, over this line where the boundary layer is formed, how much we are supposed to shift this outermost streamline so that we can have the same value which was when the plate was not there and when the boundary layer was not formed in this particular region. So here the formula for calculating the momentum thickness is like this. Again, we have the ratio of velocities. Local velocity means whatever be the value of velocity at that particular point to compare to the free stream velocity, which is basically a very important concept. So here in displacement thickness we talk about losses due to mass flow rate, and in momentum thickness we talk about taking care of losses due to formation of boundary layer, which results in loss in momentum of the velocity, and mass flow rate, momentum, and also the coming concept which is energy. Everyone has to deal with the velocity changes, right? So particularly we are concerned in this particular region, whatever losses of mass flow rate or this momentum or velocity or energy has taken place, how to recover those losses. In order to recover those losses, we try to shift the boundary layer. So by how much distance the boundary layer has to be shifted perpendicular to the surface of a plate, whereby the energy losses will remain the energy to have the same energy as that of a disturbed flow, undisturbed flow, or free stream flow over this entire length. The formula for calculating the energy thickness is given by this. So that's all for today. You are free to interact and ask questions in the section down the YouTube channel. Thank you very much. Have a very good day, and in next class we'll talk about some other important concepts. Till then, thank you very much. Good day.